So, welcome students again. So, this is perhaps the next concept that we will have to focus on, that is Gauss Law and its applications. So, first, before we proceed, let's understand what is Gauss Law. Already I discussed with you what is flux. So, when we were doing electric field lines, I had discussed what is flux. So, now, according to Gauss Law, the net flux through a closed surface is proportional to the charge present inside the surface. This is what is Gauss Law. Mathematically, I can say that E dot A is equal to or is proportional to Q, or E dot A is equal to Q by epsilon. What it means is this. Now, suppose I have a closed surface. This is the closed surface example we have already seen before. So, there was a Q, and suppose there were field lines this way. Okay, so if there were field lines this way, now in the example that we had seen, I had explained to you how the flux on the top surface and the bottom surface is 0. I had also explained to you how the flux on the two side surfaces are 0. So now what do we have? We have a flux on this surface here, we have a flux on this surface here. So when we worked out, here we saw it was equal to E dot E into A, negative E into A. Here it was positive E into A, and then we said the net flux is 0. Okay, now students, just imagine, suppose there was a charge inside. Okay, now every charge will have its own field lines. So now I'll be able to draw these field lines. So when I draw these field lines, please understand that this field line that I have represented by 1 cuts the closed surface into at 2 points. At one point it will give rise to a positive flux, on the other point it will give rise to a negative flux. On the other hand, every field line which is originating from this charge here is going to cut the closed surface at exactly 1 point, giving rise to a positive flux. Okay, so what Gauss Law is saying that if you have a closed surface, the net field lines, there are field lines coming in and there are field lines from within the surface which are going out. The net number of field lines which are coming in or going out is proportional to the charge. But number of field lines is what we are talking of as electric flux, which is not quantified. So we'll rephrase it and say that the net electric flux through a closed surface is proportional to the charge present inside. Now electric flux is represented as E dot A. So E dot A is proportional to Q, and the constant of proportionality is epsilon. So E dot A is equal to Q by epsilon. Okay, now this is what I can say when I am talking about discrete charges. In fact, I can say summation, so that I am adding up all the E dot A's which are possible in that closed surface. Okay, now in case of a continuous charge distribution, I can replace that summation with an integral, and I can say that surface integral, the circle here indicates surface integral. So surface integral E dot A is proportional to Q, or surface integral E dot A is equal to Q by epsilon naught. Okay, so what this does is, this tells you whether there is a charge which is present inside the surface or not. Suppose there are these 5 charges which are present here in space. Let's talk of any point here. Any point here, the electric field will be equal to the sum of electric fields due to the individual charges. Assume these are all positive charges, so the electric field here will be the sum. Electric field at point P is equal to the electric field due to 1 plus the electric field due to 2 plus the electric field due to 3 plus the electric field due to 4 plus the electric field due to 5. There are 5 charges. So this is what it is. But suppose I have a closed surface here like this, then the net electric flux will be equal to integral of E dot dA. Now this will become equal to integral, surface integral of E dot dA. So that will become surface integral E1 plus E2 plus E3 plus E4 plus E5 dA. So I hope this you are able to understand. Now I can remove the brackets and rewrite that as E1 dA plus integral E2 dA plus integral E3 dA plus integral E4 dA, and so on. Now what Gauss Law tries to say is this. Look, charge 1 is outside of this surface. So this will not give any electric flux, or this integral is equal to 0. Here charge 2 is also outside the surface, so this will also be equal to 0. Charge 3 is also outside the surface, so this is equal to 0. Charge 4 is within the surface. Charge 4 is within the surface. Now because charge 4 is within the surface, the flux due to charge 4 will not be 0. Again, charge 5 is out of the surface, so it will be 0. So integral E dot A on this will simply be equal to integral E4 dA. Okay, so that means the net flux within any surface will only depend upon the charge which is present inside and will not depend on the charges which are present outside. Okay, so I hope this concept you are able to understand. This is what is the essence of Gauss law. If you're still not able to understand, look at it this way. Suppose there is a flowing water here, and within that flowing water there is a tap. Now if I want to and that tap is throwing water in all directions. If I want to understand how much water is coming out of the tap, if I just catch all the water which is there within, so what I do is I take a closed surface and then I try to place that closed surface within the water. Now some amount of water, because of the flowing river, is coming in and going out. So that is not the water which is coming out of the tap. Okay, so the excess water is the only water which is coming out of the tap. So that is what Gauss law says, that there are, so now if you look at this charge, there will be field lines going this way, there will be field lines going this way. So all these field lines will be cutting this, but one will give rise to positive, other will give rise to negative. One will give rise to positive, other will give rise to negative. So the net flux due to Q5, Q3, Q2, Q1 is 0. The net flux will be there only because of the charge which is there at Q1. Okay, so this is the essence of Gauss law. So let's look at a few applications of charge Q here. I am asking you, okay, what is the electric field here? Okay, so now to find out the electric field here, what I do is I draw a Gaussian surface. A Gaussian surface is a surface so drawn that the electric field at each of these points is the same, because this distance is the same. This distance is the same. So this R is the same. Because this distance is the same, the electric field lines will be the same. Because this distance is the same, the electric field will be the same. Okay. So according to Gauss law, surface integral E dot dA is equal to Q by epsilon naught. Now because E is the same at all the points, I am bringing it out of the integral. So I will get E integral dA is equal to Q by epsilon naught. So from here I can say that E into this closed surface that we are talking of, surface area of a sphere is 4 pi r squared. So E into 4 pi r squared is Q by epsilon. So from there I can say that the electric field is equal to Q divided by 4 pi epsilon naught r squared. I just shifted this down. Okay, so what I have done now is I have used Gauss law and I have proved Coulomb's law. Already we have seen, according to Coulomb's law, the electric field at any point due to a charge is given as Q divided by 4 pi epsilon naught r squared. Now here we have used Gauss law and then proved Coulomb's law. This is the kind of question that you will get, a direct question that you will get using Gauss law, prove Coulomb's law. Please understand that Gauss law is a more fundamental law. Gauss law has universal application, just that we don't know adequate maths to find out these integrals in all situations. So we may not be able to find out these integrals in all situations and answer, but otherwise this is what Gauss law is. Okay, then let's look at some more applications. Suppose I have a line charge here. Okay, so this is an infinite line charge. Let the charge density be lambda. Charge density means what? Suppose I have a wire. Suppose this wire is given a charge Q and it has a length L. Then the charge density lambda is equal to Q by L. Okay. Now the question is, this is infinitely long. At any point you want to know what is the electric field. So if I want to know what is the electric field, the first step is to draw the Gaussian surface. So I draw a cylindrical Gaussian surface. Again, why did I draw a cylindrical Gaussian surface? Because at all points on the cylinder the electric field is the same. Why is it the same? Because it is at the same distance from the line charge that we are talking of. Okay. So if I apply Gauss law, integral E dot dA is equal to Q divided by epsilon naught. Right? This is what is Gauss law. Now students understand that the electric field here will be in this direction. On this surface and on this surface the electric flux is 0. So this closed surface, I am removing this and this because the flux is 0. Why is the flux 0? Because the electric field is in this direction. The area vector, remember I told you the area vector is perpendicular to the plane. So the area vector is perpendicular. Because the area vector is perpendicular, the electric flux here E A cos 90, and cos 90 is 0. So the electric flux on this surface that I have shaded and on this surface that I have shaded is 0. Okay, so now the electric flux on the curved surface. So again, because E is the same, I can bring it out of the integral. The area of the curved surface will be equal to the circumference 2 pi r into the length of the curved surface. So we are talking about the area of the curved surface of the cylinder. Now this will become equal to lambda into L divided by epsilon naught. So here the L will get cancelled and I will get the electric field is equal to lambda divided by 2 pi epsilon naught r. Epsilon naught r. So this is the electric field at a distance r from a infinitely long line charge. Okay, so I hope you are able to get it. When you get questions of this kind in your exam, they'll all be direct questions. You just have to plug in the values and answer. That's all. So let's look at some more applications. Suppose this is a shell. SHELL, a shell. A shell is a hollow sphere. Okay, so the question is, what is the electric field inside a shell? So if this is a shell, I have drawn a Gaussian surface here. So the shell is a hollow, so there is nothing here. There is a charge only on the shell. So inside there is nothing. So if I apply integral E dot dA is equal to Q by epsilon naught, what is the charge Q? Q is equal to 0. So if Q is equal to 0, integral E dot dA will give you a 0. So if integral E dot dA will give you a 0, what can I infer? Area cannot be 0. So what can I infer? The electric field is 0. So the electric field here on this shell will be equal, inside the shell will be equal to 0. Okay. Now suppose I have a point outside. I ask you what is the electric field at this point. Now suppose I draw a Gaussian surface. Now there is some charge inside. So by the same logic that we have done before, I can say E dot dA is equal to Q by epsilon naught. So now E is constant. So E into 4 pi r squared is equal to Q divided by epsilon naught. So from here I can say that the E vector is equal to Q divided by 4 pi epsilon naught r squared. Okay, so students, what we are saying is, if there is a hollow sphere and the hollow sphere is charged, all points inside there is no electric field, all points outside the charge behaves as if it is located at the center. These are two very important laws which are called the shell laws. This is something, the foundation for which is laid also in the chapter on gravitation. So let me rewrite it. 1. All points inside the shell, all points inside the shell have no electric field. At points outside, the charge behaves as if it is located at the center. Okay, so these are what are known as the shell laws. Very important. All these come from Gauss law. Okay, so I hope you are able to understand this. Suppose I have a plane. and there is a charge distributed on it. So this is what we will call as a surface charge distribution. So suppose there is a plane, on this there is a charge Q which is distributed. If the area is A, then I can say Q by A is sigma the surface charge distribution. So if there is a surface charge distribution on it, I am asking you now what is the electric field at a distance d from the surface. To see the side view, this is how it is, and we have a point D here. So the question is, what is the electric field at a distance d from the surface of a charged plate? Okay. In such a case, what I am going to draw now is I am going to draw a Gaussian surface of this kind. Now this Gaussian surface goes on to both the sides. So see, if this is a plane, there is a Gaussian surface here, a cylindrical Gaussian surface here. So this surface will go on to both the sides because the field lines will be going perpendicular to it. So now when I look at this, now on this side the electric field is this way. On this side the electric field will be this way. I hope you are able to understand this. Now when I apply Gauss law, integral E dot dA is equal to Q by epsilon naught. Please note, on the side walls the area vector will be perpendicular. On the curved surface the area vector will be perpendicular. So there is no flux. Flux is there only on this face and on this face. Okay. So because they are equidistant, I will say E is constant. Suppose this area is A and this area is A. So the total flux on this and this will be 2 times E into A. Students, here the area vector is in the direction of the electric field. Here the area vector is in the direction of the electric field. So the net flux will not be 0. The next net flux will be 2 times E into A. So this 2 times E into A will be equal to Q by epsilon naught, which will become equal to sigma into A, charge density into area divided by epsilon naught. So the area will get cancelled, and I will get a very important relation that the electric field is equal to sigma by 2 times epsilon naught. The electric field is equal to sigma by 2 times epsilon naught. Where are we going to use this? Specifically, we will be using this inside a capacitor. So in a capacitor, you have 2 equal and oppositely charged plates. So now what is the electric field inside it? So the electric field inside it will be 1 sigma by 2 epsilon naught because of the positive plate, another sigma by 2 epsilon naught for the negative plate. So total it will become sigma by epsilon naught. So this is the electric field inside a capacitor. An important thing, remember, when we were doing point charge, the electric field is equal to Q divided by 4 pi epsilon naught R squared. When we were working with a line charge, the electric field became lambda divided by 2 pi R epsilon naught. Now when we are discussing it with a plane, the electric field E is equal to simply Q divided by let's say sigma divided by epsilon naught, or rather 2 epsilon naught. Here it depends upon distance. Here it depends upon distance. Here it is independent of distance. Here it is proportional to E is proportional to R power minus 2. Here E is proportional to R power minus 1. Here E is proportional to R power 0. So remember, the electric field due to a system of charges may be proportional to R power minus 2, may be proportional to R power minus 1, may be proportional to R power 0. And students, if you remember what we did for a dipole, there the electric field was proportional to 1 upon R cubed. Yes, if you remember axial point and equatorial point, R power minus 3. So remember, the electric field can be proportional to R power, inversely proportional to R power 3, inversely proportional to R power 2, R power 1 and R power 0. All these are possible in different situations which we are learning in our syllabus. Okay, so this is about Gauss law. We can do many more questions based on this. One simple question which I like to do all the time is this, that suppose I have a cube, and inside the cube, suppose there is a charge Q. So what is the flux through this cube? So there are 6 faces here. The electric field at each face will be the same because the charge is at the center. So I can say that 6 times E into A is equal to Q by epsilon naught. So first, the flux through the cube is equal to Q by epsilon naught. Now they can ask me what is the flux through each of these walls. So the flux through this wall will become equal to Q by 6 epsilon naught. I hope you are able to get it. Similarly, suppose I have a cube here and at one of these corners I have a charge. So now they can ask me what is the flux on each of these, on this face or on this face or anything. So the way I go ahead is, look, I'm going to put one more cube here. Similarly, I'm going to put cubes so that this charge is completely surrounded. I know this. So this charge should be completely surrounded. So how many cubes should I put? I have to put 4 at the bottom and I have to put 4 at the top. Then this will be at the center. I hope you are able to imagine. Okay, just to make it easy for you, it will look something, I am talking about this one. But I have drawn 4 here, 4 will be there at the back. Okay, so there will be totally 8 cubes. Now, when we have 8 cubes, any one area will be, going by this logic itself, for an area A equal to 2 times A square, the flux will be Q divided by 6 epsilon naught. Purida, this point, there are 2 areas, one area at the bottom and one area at the top. So this area will be totally 2 times A square. So for 2 times A square, the flux is equal to Q by 6 epsilon naught. So for just one surface, because initially I had just one cube, so for this surface alone it will be half of this. So the flux here on this surface, if I draw this diagram this way, the flux on this surface will be equal to Q divided by 12 epsilon naught. Okay, so I hope you are able to understand it. Totally there are 8 cubes. On 8 cubes will have 6 faces. Each face will have a total area equal to 2A square. There is one face here, one face here. So 2A square. On 2A square the flux is Q divided by 6 epsilon naught. So on single cube the flux will be Q divided by 12 epsilon naught. Okay, so I hope you are able to get it.